here's where we first take your blood spot and we put it in a tube. We put it in one of these ceramic pre-filled bead tubes. Sorry, these are metal, not ceramic. We use ceramic for proteins. So the idea is that this is a completely inert thing that takes your dry blood spot along with methanol and an internal standard that we tag it with to quantify the metabolites later on. It essentially will take that and precipitate proteins, precipitate the DNA. We're able to then remove that and then just keep the internal standard and the metabolites from your sample. So we do that first by taking the dry blood spot. We biopsy punch a 6mm hole. We only need one of them actually. We keep the other blood spot in case there's any issues with data collection. And if the data look good, then we throw away your blood. We don't want to keep it. We don't have space for it. Get it out of here. So the first thing we do is homogenization. So we take that tube with the metallic beads, your blood spot punched out, the methanol and internal standard, and then we go and homogenize it. And we'll see the homogenizer, it's a bead mill, right? And it essentially turns that into a slurry. It's unrecognizable. It goes from paper and some water to a slurry. And then we will take that slurry, we'll come over here, and we will, in ice water, we'll essentially float it in a sonicator, and then we blast it for 20 minutes at 100% power, 80 kilohertz frequency, and we do it in ice water, obviously, because when you're sonicating things, it gets hot. We don't want the sample to heat up. So it's an ice bath floater. The goal here is to sonicate the actual metabolites that are bound to protein still. If there's any protein still left over after that precipitation step that we haven't removed or bound up into a precipitate at the bottom of the tube, these are now going to, with ultrasonic waves, pulse against that protein and cleave off any metabolites. So we're able to actually look at total metabolite levels by sonicating, right? After we're done with sonication, we will put that into our high-speed centrifuge. We spin this at 22,000 G, incredible speeds. And now what we're doing is we're completely separating the liquid portion again, so that slurry goes again from being unrecognizable kind of like paper watery slurry now to all the papers on one side because it's centrifuged, and all of our liquid material that contains metabolites, proteins, lipids, DNA, everything is on the other side, right? And it's triple layered. So we have one top layer that's all lipids. We can actually extract that for lipidomics, something that we may be doing in the future with a separate panel. And the metabolite layer is the middle layer. So you'll see kind of a milky top layer, a very clear middle layer, and then just paper precipitated at the bottom. We extract that metabolite layer, and then we go to dry it. We'll take a tour of the drying as well. We go to the dryer at 37 degrees. We dry that sample out for about 2 hours, 120 minutes, depending on batch size. If it's a really big batch size, we'll increase that until we get very dried residues. So there's nothing in that tube but this white powder. Those are the metabolites by themselves. And then we reconstitute that with a heating block. So then we will sit that Eppendorf tube in our heating block. We will heat that up to 60 degrees Celsius. Once we've heated that up, we put derivatization reagents to it, and we create what are known as trimethylsiloxane derivatives. We are changing slightly the chemical structure of that metabolite. We're doing that because we're trying to actually diminish its boiling point, right? These metabolites will boil at anywhere from 250 to 390 degrees Celsius. We want to ensure that they are boiling at 250 degrees or less. And that's because we want to analyze it in the gas phase. And this will become more apparent when we get to the mass spec room. But the idea is that we want to change the structure of the metabolites, to change their chemistries, change their boiling points, so that when they're injected into the mass spec, they immediately vaporize at 190 degrees to 250 degrees Celsius and are carried on a helium cloud, on a helium medium, on what's called the mobile phase, through this chromatography column. We separate that by retention time, so it's a time-based separation, and then we sort the metabolites based on weight through the mass spec. That's a mass to charge ratio. So we do two-dimensional separation, and we'll talk about why we have to do two. Why not just put them on mass spec? Why do we need chromatography? We'll talk about that in a little bit. But yeah, this is where most of the work happens. You were talking about, we won't do derivatization, but on the first day we'll derivatize a batch of 50 of them. The second day we'll do another 50, and so we were able to work our way through. So within 6 days we've done that entire batch of 350 at a time. So this is our reagent fridge. This is a very sterile, incredibly sterile fume hood. We also have our microscopy equipment, cell counters for assessing viability, and temp-controlled stations here. So we do, research proper research and not on customer samples. And so this is the room that we utilize to grow those cell lines, adopt different experimental conditions, and then sample those cells for metabolomics. We're growing corals in that room and then popping off nubbins and doing analyses, and our hypothesis is essentially this. This is published as of now in PeerJ, so if you Google my name, corals, this is going to come up. And it's a really fun look at how insulin signaling is preserved through our highest common ancestor, which actually happens to be the corals. And so we looked at them and we saw that there was a dysregulation in insulin signaling given their metabolite levels. And what we hypothesized is that this coral is living in a symbiotic relationship with the phytoplankton around it. The phytoplankton are producing this insulin-like protein that is binding to the corals and helping them metabolize glucose. So what causes coral bleaching? We know it's associated with rising ocean temperatures and pH, but what we've discovered in our research that was recently published was the rising temperatures and pH are actually affecting the phytoplankton. And as the phytoplankton are dying, the coral are losing the symbiotic relationship that helps them metabolize insulin by the ILP protein that's being produced from this phytoplankton. And so as the phytoplankton die, we get coral bleaching. That's the phenomenon of coral bleaching, and it has to do with coral diabetes. So we always joke that we're going to just dump metformin in the ocean, see if that helps. Yeah. But here we actually use very sensitive and specific lasers that poke at incredibly low nanometer diameters, and we take let's say rhodopsin protein. So for instance, we're doing a study on narcolepsy or night blindness. Why doesn't rhodopsin regenerate faster, and why are people having night blindness? So we'll take a rhodopsin in different genetic mutations, and we will essentially hit it with laser. We'll watch it cleave and then reform itself, and then we are looking at reformation times and trying to figure out what metabolites are leading to delayed reformation times. As rhodopsin is delayed in reforming in the retina, then so we use this very expensive $250,000 laser in there, and we have to have a special setup where if they're using a dark room, you can't come in.
Yeah, this is kind of my side of the lab. We do microbiome stuff here, so things are a little bit more chaotic, but basically this is the very same, I think this is the same bead mill that you have in the dark room. It's the Fisher brand bead mill 24 pennies. Basically, we put the sample in bead tubes, and we run it through our process to really break down the sample further. For my work with the microbiome, we're actually looking to lyse the microbes so we can get at their genetic material.
Spin it up.
You want to get a run?
Yeah, get a quick run, a 20-second run or something. So it's only 20 seconds, but as you can imagine, when it's in this tube, your sample's cut out, it's punched out. It absolutely obliterates your sample. In 20 seconds, it creates this sludge that you can't even tell is paper. And then we treat that sludge, and then we use high-speed centrifugation to separate that from the metabolites. All good? This is a triple quad machine. We'll talk about some triple quad studies as we keep going. This is a GCMS actually. This is another GCMS. It is just like ours, same column, and we'll talk about the anatomy of this machine when we get it. So this is a shared storage. It's water purifier. It's spitting 18 ohm water. And this is our dryer section. So we have two dryers. We can use a liquid nitrogen snap dryer when we want to snap freeze cells without causing any sort of cold shock to them and changing their metabolism. And then this is what your samples are dried on. So we will essentially put it on here. We will start the pump, the condenser, and the rotor, and at a very temperature controlled 37 degrees Celsius to prevent any sort of unintended reactions. We will dry your samples until they are just metabolic residues. They're this white powder at the end of the analysis. Okay, so this is our mass spec room. This is where the clinical analyses happen. Yeah, so on the left-hand side, you'll see a vacuum culture AU480. This is a chemistry auto analyzer. It's essentially a chemist in a box, right? This is like a bunch of mechanical arms. You feed it reagents in these tubes, And then you say, okay, I want to get hemoglobin A1. All of this, these tanks, everything, this is old tech. It's really just a mechanical auto analyzer, and it costs a ton of money, and it returns, I think, 29 parameters. That's it. And so this isn't what we use. This is our mass spec. So right now, this is the software and the computer and everything that is utilized in the analysis of your sample. We have some samples on the arm, and then we have this needle. And this needle will go through some washes between injections to cleanse the needle and the injection site. And then it will sample. We can set up a workflow, and we say, okay, we have 50 samples. We want you to run this method of data collection. And the methods are very specific. We are looking at controlling the injection temperature. We're looking at the temperature ramp in this oven. So when this is injected, it vaporizes immediately at 290 degrees, right? It vaporizes because we have changed the chemistry of this molecule to be able to do that, right? And then it is injected into this top column here. There's an injection point. There's an injection point right under this arm, and that's the inlet. So the needle will sample 5 times, making sure to mix up the sample, and it will inject it into this inlet. And this inlet, don't touch it, it's very, very hot, obviously, as I mentioned. All right, we're good. This is the volume of sample that we inject. You can take a look. This is an incredibly small volume. We take out 70 microliters. Of this 70 microliters, we inject 2 microliters. That's all we need to sample the blood. So when it gets injected into this inlet right below here, it's heated up at 250 degrees Celsius, 290 degrees Celsius, and then it is coming out of this. This is not a copper wire. This is hollow. It has a nanometer diameter, and it has inside that column, it has these chemical protrusions, specifically has carbon-18 poking out. What this does is it takes all of these molecules and it interacts variably with them. Each one of our 126 molecules comes off of this machine at a different time, right? So from the start of the run, which is about 3 minutes in, to 60 minutes in, they're all eluting off of this column at different times. Because their chemical structures, they react variably with the inside of that column, right? So as it's injected, here we have our research grade helium that's pumping at 100 psi, good. And it's going to inject, it's going to vaporize, the helium will come along and carry it on this stream, the mobile phase, and that mobile phase interacts variably with the solid phase, which is the protrusions, the carbon-18 protrusions in that column. Depending on the chemistry of that molecule, it may come off this column quickly, it may come off this column in a delayed manner. The earliest thing to come off is about 3 minutes. The latest comes off at about 57.5 minutes, okay? And so this is 30 meters long. It has to go through 30 meters of separation before it comes out. And then once this comes out, I'll let that heat up. Yeah, it should be up to about 60. Once this comes off this column and it goes into the mass spec, so this is the chromatography part. It comes off this column, goes to this mass spec. Then we have a filament here, and that filament just kicks off electrons. All it does is it lights up and it kicks up electrons. So as the gas stream containing your sample comes off the inlet, it is going to be hit perpendicularly in this orthogonal manner by the electron beam. And this is known as electron ionization. You can see the EI source here. It lights up when it's working. It's very impressive. And it will essentially light up and it will hit your sample and ionize it. We want to ionize this sample because the mass spec uses AC and DC to control ions in its path to the detector. So we can tell it, hey, eject all of these molecules from the quadruple, eject them, don't let them reach the detector to be counted if they have a certain mass to charge. We can selectively filter for these metabolites, but we can't do that if these molecules aren't ionized. If they have no charge, there's no way you can apply AC and DC to control their movements, right? So that is the mass spec. I'll leave that off. Make sure we get to 60 here. Give me the ready signal, and we'll do a quick injection. And before that's loaded, I will show you why do we use 2 two separation techniques. Why can't we just do mass spec? Why can't we just do mass spec? Mass spec is an incredibly powerful tool. Why not? Why do we have to do some sort of chromatography? Well, take a look at this. We have glycine and we have putrescine. Both of them weigh 174 Daltons. They weigh 174 atomic mass units, right? If we were only to use mass spec, we would not be able to tell them apart. But we know that glycine comes off of that column in 9 minutes, and putrescine comes off at 12 minutes. So the system using this machine knows, okay, I'm looking at all these signals. I looked at all these signals from 3 minutes down to 57.5 minutes, and I'm scanning a range of 60 to 500 Daltons, mass charges, mass M to Z range. I know that if I just look at the mass to Z's, I'm gonna see a bunch of 174s, I'm gonna see a couple of 147s, right? Methylmalonic acid and succinic acid both have a mass to charge of 147. The former, however, is eluted off that column at 9.4 minutes, and the latter is at 10.7 minutes, right? So it knows what time to look at whatever's coming off this column at that specific time. If it sees that peak, it calculates the area under that peak as the quantity or the abundance that was detected for that metabolite in that sample. And this goes on and on. There's tons of metabolites, and it's very, very specific, right? So even when we look at something like 3-methyl-2-oxyvaleric acid and ketoleucine, they both have a mass to charge of 89. One comes off at 9.382, one comes off at 9.315. Even the slight differences it is able to detect. Look at that mass to charge peak at the correct time, quantify the area under the curve, that's the quantity of that metabolite. So we do this two-dimensional separation because mass spec, although very sensitive, able to get levels of these metabolites with a 2 microliter injection, it's not specific. A lot of things give off those signatures, and we need to separate them. And there's other separation techniques. There's liquid chromatography coupled to mass spec. There is capillary electrophoresis coupled to mass spec. There is two-dimensional GC, where you do 2 phases of gas chromatography with different chemical columns and then mass spec. But that is essentially the reason we do this. So how does it work? Really easy. Run sequence, run sequence. So now it's going to go, okay, checking all the system health. Let's make sure this is, everything's good. Okay, we're going to initialize. Do you want to wait? Do you not want to wait? There's the pre-run. I'm going to set the solvent delay. You essentially want to set a solvent delay because we want to make sure the mass spec doesn't turn on for 3 minutes, because the first 3 minutes are just junk. It's just junk coming off that. There's no need to detect it. And in fact, it deteriorates the lifespan. So right now it's doing some washes. It's going to say, all right, there's my wash. Or actually, it doesn't need to do one. Maybe it's the first injection. No, so it's going to still wash in there we go. So it's going to pool 5 times. So it's mixing up that sample, making sure that if the sample was put on that arm hours ago, which it was, there's no sedimentation effect. It's getting a good sampling of that. And then it'll come down and inject into the inlet. And now we're off to the races, right? So it's collecting all of this data, and then when we collect that data off the mass spec, we tell it, okay, using what you know about where these compounds have come off, and how do we know those compounds have come off? We've run the standards, right? We have standards for them in our chemical library. Where we take a 99% analytical standard, different concentrations, we inject it in here, and we view the response of it, right? We confirm that we know there's nothing else in the sample. It's a pure standard. We confirm what the database is telling us from the HMDV. This is where the peak should be at this time. We confirm
it's a quality assurance program.
Well, yeah, of course, this is quality control. Yeah, absolutely. So now it's going, here's the chromatography data collecting. And then depending on the run, we may or may not see this electron beam pick up. It'll start to glow, and that's the filament. Once it starts to glow, it's the filament really gearing up. This column it's a time control. So we use temperature and changes in temperature to speed up or slow down how fast these molecules are coming off of the column. It starts at 60 degrees, and it increases at a rate of 10 degrees Celsius per minute until it gets to 325 degrees. And and then it'll actually hold that for 10 minutes because it's baking off any sort of columns, any sort of metabolites off the column to make sure that it's ready for the next injection. So the system is collecting data, but also at some point, once it knows everything's eluted off this column, it's going to start preparing for the next injection. So, any questions? I mean, this is a lot of information. I'm sure you have some questions about mass spec science. Don't worry, we have an entire talk on mass spec, so you're going to get a lot of peaks. And
well, this was developed 20 years plus, so I'm sure that...
Yeah, oh yeah, even further, right? Like, I forget his name. Oh my gosh. Okay, well, this is where mass spec science comes. These are validated techniques. When we talk about what did Theranos do wrong? I'm sorry, I had to say it. I'm so sorry.
No,
What did Theranos do wrong? These technologies existed.
Yeah.
Theranos was a fraud because we trusted a high school graduate to take advanced engineering and take a chemistry autoanalyzer and put it in a little box. Miniaturization at the expense of validity is her fraud, right? Insisting that these things are available in your doctor's office right now, that's the fraud. Where we say, okay, we can't do that. We can't. There is a whole miniaturization mass spec movement where we're trying to do that. It's going to take a while before we can do that. And it's probably only going to be able to run a few compounds. It's going to be a miniature machine that is just for breast cancer or something like that. So there's the filament literally going, okay, I'm creating a constant beam of electrons to ionize this sample. So that is the mass spec. See it, Greg?
Yep.
This is what you're consulting on.
Okay.
So when they have any questions about data accuracy, you saw the ion beam. Yeah. Okay.
And then you send it to the guy and you use the screwdriver.
Yeah, so we have two things here. And so this is really noisy because it's not deconvoluted through time. This is really noisy. I'll show you a three-dimensional spectra in a talk later, and you can see how each peak, or you can see the back of your own report and see how each peak is presented, right? We show that in a three-dimensional spectra. So you have retention time, you have massive charge, and you have retention. We hit it with nitrogen, we produce other satellite peaks, and by getting a base peak and satellite peaks, we get extra specificity. So, like for instance, we'll have two compounds that have 147 mass to charge, but we know that they have the same weight because they have the same atoms, or that they have the same weight because the same molecular weight is there, but the atoms are different, the molecule is different, it's an isomer, right? So we can split that up and then see the base peaks, and every base peak has a different fragmentation pattern. So we need to get that specificity to go up to 339 metabolites. So this is where we store samples. I mean, they're actually very stable at room temp, but we always like to do any sort of long-term storage in -80. This is where all of Joe Dispenza's samples are being housed. So we finish them. Then we have a -20 for short-term storage. As I mentioned, we do that, like, derivatization to dried residues. If we're working in a very large batch, these will keep them safe for about a week at -20. And then we have a 4-degree, which is basically for reagents and everything else that we keep here. So this is kind of fairly standard. Actually, this is the lab that, before I was a postdoc in this lab, they only needed this because they're cell scientists. But for metabolomics, we need different temperatures. So they had to, in addition to paying my salary as I came on as a postdoc, they bought 2 other fridges basically just for me. So very kind gesture by Professor Klein Theriome.